In this video, you will learn about deep convolutional networks, CNNs for short. In this video, we will review 1. How CNNs build features. 2. Adding layers. 3. Receptive field. 4. Pooling. 5. Flattening and the fully connected layers. A convolutional network, or CNN, pictured here, is a neural network with special layers. The model classifies an image by taking a part of the image. Each input image will pass it through a series of convolutional layers with filters, pooling layers, fully connected layers, and while applying activation functions to classify an object. Convolution and pooling layers are the first layers used to extract features from an input. These can be thought of as the feature learning layers. The fully connected layers are simply a neural network. Both are learned simultaneously by minimizing the cross-entropy loss. How CNNs build features. If you recall, the hog feature used Sobel kernels to detect vertical and horizontal edges. Looking at these kernels, we see the vertical edge detector kernel looks like a vertical edge, and the horizontal edge looks like a horizontal edge. We can represent hog with a diagram that looks similar to a neural network. We replace the linear function with a convolution, and we have the squaring and square root operations. In a CNN, we have neurons, but the kernels are learnable parameters. The activation functions, in this case ReLU, are applied to each pixel. Instead of an activation, the output is an activation map or feature map, similar to a one-channel image. Like the hog's Sobel kernel, each kernel of a CNN will detect a different property of the image. For example, this activation map shows this kernel detects regions around the dog's eyes. This kernel picks up regions around the mouth. Usually, each output channel is smaller. We use multiple kernels analogous to multiple neurons. If we have M kernels, we will have M feature maps. For each map, we apply the convolution plus ReLU. Generally, we'll use clear squares to represent the feature or activation maps. A grayscale image can be seen as a one-channel input. If we have M kernels, each feature map will be a channel. Therefore, we will have M output channels. Adding layers. We can also stack convolutional layers. Each output channel is analogous to the neurons. Like a neuron, the input of the next layer is equivalent to the output of the previous layer. Here we have 3 outputs. The next layer will take 3 outputs as inputs. If this layer has 2 outputs, it will output 2 feature maps. The next layer will apply a convolutional kernel to each input, then add them together, then apply an activation function. The neurons are replaced with kernels. The previous layer has 3 output channels. For the first input, we apply the convolution and activation to the output of the first channel. We obtain the feature map. We repeat the process for the second input channel, adding it to the activation map. Repeating for the third input channel. The process is repeated for the next input. We can process color images by having 3 input channels. Just like a neural network, we can stack layers using the 3D representation. We can also represent them with these yellow boxes indicating the kernel size and the number of channels. It's helpful to look at the kernels to understand what the different layers are doing. If you recall, the Sobel kernels looked like they detect vertical and horizontal edges they were trying to detect. Consider a CNN used to see faces. The kernels in the first layer look like edges and corners. The second layer looks like parts of the face. The final layer looks like faces. We see that adding more layers builds more complex features. Receptive field is another important factor in CNNs. Receptive field is the size of the region in the input that produces a pixel value in the activation map. Consider the following pixel in the following activation map. Its receptive field is given by the larger the receptive field, the more information the activation map contains about the entire image. We can increase the receptive field by adding more layers. This requires less parameters than increasing the size of the kernel. If we have one layer, the receptive field would be the following region. Adding a second layer increases the receptive field further. Pooling. Pooling helps to reduce the number of parameters, increases the receptive field while preserving the important features. To make it easier to understand, we can think about it as resizing the image. Max pooling is the most popular type of pooling. Consider the feature map. We apply max pooling with dimensions 2 by 2. It takes the maximum pixel value, and we get a smaller feature map. Pooling also makes CNNs more immutable to small changes in the image. We have two images. They are identical, but one slightly shifted. Let's see the activation map after max pooling. We apply max pooling in the first region and repeat. We see the activation map output is now identical. Finally, we have flattening in the full connected layers. We simply flatten or reshape the output of the feature learning layers and use them as an input to the fully connected layers. For example, if the output of the max pooling layer is 7 units of width and 7 units of height, we flatten or reshape the output. This is analogous to a feature vector. This is the input to the fully connected layer. Each neuron has the input dimension as a flattened output. For more channels, we apply the similar procedure. If we have 32 output channels, each channel is 4 by 4, for a total of 16 elements. As there are 32 channels multiplied by 16, we have a total of 512 elements. We flatten or reshape the output to have 512 outputs. As a result, each neuron will have 512 input dimensions.